Okay, so as I go along today, I want to share with you my thoughts on data, first part of data science. All too often though, we think about model building, we think about machine learning, right? We think about the aspects of data science that are new and changing rapidly in the last couple of years. I want to bring you back to some of the basics of the underlying data, because in most really production environments, real science, real industry, the underlying data you're working with is incredibly valuable. And so it's also incredibly governed, either because of IP concerns or because of regulations. And beyond that, it's in a number of different silos, right? A whole host of flavors of data management systems. And by far, the most energy, time, investment in any data science project is around gathering the data, curating it, securing it, right? And this aspect is changing dramatically. I've been working in this space for 30 years now. And I think it's fair to say that the last 5, 10 years are seeing a bigger change in the underlying technology for data management than any time prior, up to perhaps the relational model with COD in the 70s, okay? So this is what I want to tell you about today. The biggest change has come from the cloud. And what is the single differentiating aspect of the cloud? Elasticity. Where earlier you bought maybe 100 servers and you were stuck with that configuration, the memory compute ratio, for example, the number of machines, for a long, long time, right? Today, you can go to the cloud and rent compute and storage. And you can get as much or as little near instantaneously of either, right? That changes the game. I frankly did not expect when I moved to Yahoo, Microsoft. Now, I was gung-ho about the cloud, which is why I moved, but I did not expect the pace at which things would move, right? And that has had a corollary effect. As data management technologists, our core technology, our SQL Server, for example, which is, number 1 or 2, depending on how you count, as an on-prem data management package. It was built for a different world. It was built for a fixed resource configuration. It was not built to adapt elastically to changing resources. And that has forced us to re-architect from the ground up, right? And the changes in a piece of software that's responsible for close to $10 billion a year of revenue, it's near unthinkable, right? And that has implications for you as a user, and I'll try and share some of that with you. And even bigger changes coming. Edge. When you think of edge, think about cars, think about planes, think about elevators, right? Soon, I believe, you will see kiosks, right? Those old red phone booths, maybe something a little different in looks, but functionally, on every corner, there may be a data kiosk. And what does that do? Act as an intermediate point between a centralized cloud, right, and the stop and go and the compute infrastructure inside that stop and go. So what that's going to do is essentially bring the power of the cloud to mom and pop stores. It's just going to democratize all of those technology we're talking about that today are of most interest to the Chevrons and the Goldman Sachs of the world, right? As that happens, the notion of where data is out there in the cloud, on your laptop, somewhere in the ether, it's getting blurred, right? It's going to get complicated. Part of my story today, it's way too complicated. And so I foresee technological shifts to hide some of this from you. But a corollary of that is you don't really know where your data is. And that means increasingly there are regulations about how data can be handled as it moves through this whole expanded memory hierarchy. Okay? Machine learning. Database people have a tendency, whenever anything related to data grows, becomes popular, we suck it in. Okay? XML, put it inside a database. Right? I don't believe that's happening with machine learning. Machine learning is vibrant, a rapidly exploding community. It's going to have its own development surfaces. But I don't want you to get confused about one thing. Machine learning and data management systems are inextricably interwoven. Okay? So this is something that the moment you start to work on significant industrial strength projects, it'll hit you forcefully. As a data management technical professional, this has implications as well. Right now, we really have to think very, very hard about the implications of machine learning and one other thing, data governance. I was joking with Moshe yesterday. My text is called Database Management Systems. If I ever revise it, which I've been trying consistently for several years, right? The name will have to change. And Moshe actually suggested just dropping the base, right? And I think that's what's happening. The database management system form factor was store your data, query or transact, and manage it. That management, today with so many different data management systems as silos, if I want to specify governance policies across all my data holdings, I have to go to each and every one of them and repeat. This is not viable. And it's going to be even less viable as the trends that I just described to you play out. Okay? So what I think is happening is a new surface side by side with your typical data repositories, your DBMSs, your Hadoops, your Excel spreadsheet repositories, side by side with all of that. You're going to have a pane of glass on which you can specify your policies. Who can see what data, under what conditions, for what purpose? And this is going to be enforced using whatever the local repository has available, but enforced nonetheless by this data governance component, right? This is not yet there. It's desperately needed. It's coming. And as we go through this talk, I'll try and touch on some of the implications there, some of what that means. What is the cloud today? If you look at various countries, those that have a lot of data centers, 30-40% of their power consumption is because of the data centers. Globally, double-digit percentage of our power consumption is in these data centers. Global warming is influenced by data centers and Bitcoin mining. Okay? Azure has 54. This is growing rapidly worldwide. Part of the reason for that is things like data sovereignty, right? Data is subject to the laws of the country where it is physically. The edge, if you think that's big, that's going to be dwarfed by what I call the cloud, by what I call the edge, right? Edge devices are going to be in the hundreds of thousands, if not millions, right? And your data is going to be cached, diffused, in some cases generated out there. When you think of your data, what you're responsible for, it's not this nicely contained bit of bytes sitting on a disk managed by Oracle or SQL Server. That is ancient history, right? Your real estate now spreads over all of this. Okay, and that vision of ubiquitous data, it's becoming cheap. The caching techniques are getting good enough that you can access it either in a big honking query running on the cloud on 1,000 machines or on your PDA, wherever you are. And this could be, your video cam showing your baby, right? That data is available wherever you are. This kind of data ubiquity, what can you do with it, right? Lots of things. At the same time, what should you be allowed to do with it? That's becoming a huge concern. How many of you heard of GDPR? Oh, good. That's a larger percentage than I usually hear. So this is the privacy law from Europe. Australia, Canada, California, many other places have started having similar laws. These constrain what you can do with personally identifiable data. That's one example. There are many, many such regulations and more coming. And those apply no matter where data is in this continuum. Okay, in this talk, I'll also touch upon some of the work with Microsoft Research and the Gray Systems Lab, which is an applied research team inside the data management group, the data platforms group. One of the nice things about Microsoft is they have long recognized the value of research and invested in it. So for this audience, I thought as I go along, I'll touch on all the things that research is actually contributing to. For the purposes of this talk, let's simplify. I'm going to discuss data in Azure in roughly 4 buckets. First, big data, data lakes. Dan Jaffrey and others spoke about this yesterday. You're familiar with it, Hadoop, right? Data warehouses. If you are in any kind of corporate setting, these are the Teradata, Exadata, SQL Server, systems. Typically MPP, tens of nodes running in parallel, right? Relational warehouses. You aggregate all the data from your operational stores, use this to power all kinds of BI reports. OLTP. These are the systems of record. TPCC benchmarks are run here. When you write a check to someone, that transaction is recorded in an OLTP system, online transaction processing system. NoSQL, Mongo, Cassandra. These are systems that have gone away from the relational model. The underlying model of data is typically an object identified by a key. And the object could be a JSON document. It could be whatever. In return for this simpler, more loosely structured representation of data, they get some things, right? And they give up some things. They give up, for example, some of the rich relational operations. You can't have elegant joins that really work magically. But the simplicity also allows you to build geo-replicated real-time systems, right? So at Yahoo, one of the NoSQL systems there, if you log in, your login has to be recorded in multiple places because if Sunnyvale falls into the sea because of a quake, you don't want to lose your Yahoo login, right? Likewise, if you travel to Singapore, but you usually live here in Houston, you nonetheless want your Yahoo account to be available. So those kinds of geo-replicated systems are good bets for NoSQL. Okay, machine learning. Where is it in this picture? Everywhere. So let's say you have data. These little cylinders denote any of the above. They are databases. They could be any of the 4 buckets we talked about. And you have some apps. Ultimately, this is where the road meets the rubber, right? The first thing you do if you want to use machine learning is train. And to train, you do feature exploration. You iterate, in fact. You rinse and repeat quite often. You finally build a model. And in the course of doing this, you try different algorithms, different hyperparameters, right? Nowadays, with things like AutoML that take away some of the tedium, you do even more. This touches data, right? This is the most expensive part of training. Not so much the algorithms you run on the GPUs, but simply the exploration, repeated, rinse and repeat, over the data to find the right features and to find the right combinations of parameters and algorithms that yield a good model. And then, of course, cross-validation to ensure it is a good model. Let's say you find a model. Happiness, it's only useful if you can score. So you deploy your model. What does deploy mean? You put it in the way of more data, new incoming data that you want evaluated through the model. You want to do inference on it. You want to score the incoming data. There are policies. Who's able to update the deployed model? I mean, a model is a piece of data. You have rights to it. And again, notice there is data. Okay? This is the data on which you're going to score. And model scoring is itself a complex process. And again, your app, your sources of data, it's live. It's not static. It's continuous. This is the complicated cycle. And keep in mind that every time you see one of those colorful cylinders, you could have not one, but a whole array of data sources of all the different types I'm talking about, right? And that complexity has to be responsibly handled. You know, we talk about referential integrity in data management. What it means is, if I have a table of employees and a table of who works in which department, an ID saying this employee works in this department in that relationship table must be identifying at all times a valid employee in the employee table. In other words, no dangling references. In this process, let me give you an analogy. Let's say you train a model. You train it using some source of data, someplace, right? Maybe this is data on Azure. You deploy it to a collection of edge devices. That model, increasingly, you will be required to justify the decisions made with that model. Okay? Are they biased? You're a mortgage lender. Is the decision you made in part based on that model biased? To justify that, you need to go all the way back to the training process, the snapshot of the data you trained on, because if your underlying population was not representative, your model could well be biased regardless of the algorithms you have. So how long do you keep the data that you used to train a model? As long as that model is deployed somewhere on planet Earth, or maybe some other planet in future, and you're responsible for justifying its use. Okay? So these kinds of regulations are in their infancy. But as they take effect, the implications will really begin to bite. Today, to be frank, while things like ML flow are beginning to think of these kinds of end-to-end challenges, it's in its nascency. Most people have to cobble together their own or do without. Okay? That has to change. Data is cutting too close to our lives. On a more geeky note, it's not just at the level of management. I'm not really going to talk about this slide. Don't worry. But if you take a piece of code that's really something you might find in a Panda or in one of your Python spreadsheets, you can parse that, turn that into an intermediate representation that's interleaved with your SQL accessing the data. Really, most machine learning models can be expressed as DNNs, linear algebra, interleaved with relational algebra. You can do lots of algebraic optimizations. Scoring can be made order of magnitude more efficient. right? And partly because of that, partly because you don't want to exfiltrate data if you can avoid it, right? More and more of scoring in particular is going to get pushed down close to the data, okay? So the nexus between machine learning and data systems is going to get much deeper very soon. It's already happening. Some of these things we are pushing into SQL Server. Okay, cloud. Let me go quickly through some of what this means for you. First off, if I have a database in the cloud, you can come rent it from me. You don't even have to buy all of it, right? You can just rent a teeny tiny database, all right? You don't have to hire a database administrator. The bar for actually using this stuff has gone down because of the cloud. What does that mean? For it to be cost effective, I'm slicing the resources on that physical machine to essentially give you enough memory, enough CPU to run your little DBMS, okay? And doing so is tricky, because if I'm going to interleave databases for everyone in this room on the same physical machine, how do I make sure each of you gets what you're paying for, that noisy neighbors don't clobber you, okay? A lot of non-trivial work. We have worked very closely with MSR, and much of this is already in there. So point number one, if you take simple things like resource governance, the name of the game in the cloud is to have a massive pool of compute, a massive pool of storage interconnected by high-speed networking, and then to rent slices of this infrastructure to people. And increasingly, we are not just renting this as memory and CPU. We are renting it in terms that are much higher level in the stack. We are renting databases as one example, okay? And that means the software that gives you that vision of a database, the APIs that conform to things like create a table, create an index, run a query, run a transaction, they need to run proportional to, quote unquote, the size that you're paying for, and do so in reliable ways, in repeatable ways, consistently with SLAs, right? No matter how I choose to multi-tenant these resources. Otherwise, it's not a viable game. And this game is only getting more and more sophisticated. Used to be that the slices I gave you were fixed. And if you wanted to resize your database as you went along, it wasn't so easy. Well, it's all a matter of time, rapidly changing, right? There's more work on how to resize those slices of a database I give you dynamically. And that is a thought I'll come back to. Here's an example where I take a database, slice it up, and let you each rent flexible, elastic pieces. There's the other direction. You have a lot of data. You want to scale up. That's a much harder challenge. I'll come to that. Okay. Indexes. Here's a different point I want to make for you. Historically, database administrators are hired by a company to sit between you, the typical application developer, and the database. When you get to large amounts of data, building the right indexes, organizing the data in a way that's efficient for the things you do with it is non-trivial, right? You can either read a book like mine or hire someone to take care of it for you. Most people choose the latter, okay? So in the cloud, if you're renting these dinky little databases, you're not going to go hire someone. If you're getting to very large databases, yeah, maybe you have someone who thinks about performance. But the truth is, this phenomenon of renting in the cloud all of a sudden means there is a higher expectation on those databases being self-organizing. Rather than having an administrator say, pick this index, the expectation is they'll index themselves appropriately. And what's more, in the cloud, subject to appropriate data ownership, visibility, I can actually see the telemetry from all the millions of databases that have been rented from me. Okay? And coarsely, I can classify your database as being similar to Moshe's. Right? And at this level, I have a level of visibility into the effect of a certain organization, adding an index or taking away an index, which I can use to self-tune. Okay? So both the expectation and the reality of the cloud means back in the day, for decades, we talked about self-tuning database systems. But ultimately, we sold these self-tuning database systems to someone else to administer for themselves. Now that we are the DBAs, that we use this technology ourselves, all of a sudden, the focus has gotten a lot more sharp. Okay? So all of this is happening. Yet another example of the same index. Let's say you have a shared internal cloud within your company, and literally thousands of people are running complex queries all the time. This is the scenario at Microsoft. Let me tell you, by observing the queries that are run repeatedly at the same time, by observing which queries have a lot of overlap, they run on the same data sets, they do, to a large extent, similar kinds of subcomputations, you can do intelligent view materialization. What does that mean? Some part of the query that Peter runs, I recognize might be useful when Paul comes along 10 minutes later. And I have a pretty good idea Paul's going to come along 10 minutes later. Right? By doing this kind of cross-job view materialization, intermediate result caching, I can get orders of magnitude savings. Again, these were not concepts that were very relevant when everyone was working by themselves on their laptop. You bring all these workloads together, the world changes. Okay. All of that, and now let's look at cloud architectures. Now, flipping from the point of view of a user, let me show you what happens to the database, the guts of it, because of the cloud. Here's the key. Storage elastic, as much as little instantaneous. Compute elastic, as much as little instantaneous. The first generation of our systems, we basically rented virtual machines, stuck the existing database software in there, added monitoring, added patching, voila, cloud database. Okay? But as I said, those stacks were not designed to run in this kind of environment. To take advantage, and if you don't take advantage, your competitors will eat your lunch. This is an intensely competitive space. We're all racing to build cloud-native architectures. Okay? The key challenge is the network. Network latencies, depending on the workload, network bandwidth. If you don't hide those, you're toast. Because historically, database architectures have assumed that the hardware is gold-plated. Robust, as fast as it can be. You cache up the wazoo. when you do a transaction, right, your decision that I debit this account, credit this account, either both happen or neither. That means the decision of what to credit and what to debit, which is made in the compute tier, and the actual commitment of that decision, recording that so that if something fails, you still are able to go back and redo that, the so-called write-ahead log for those of you who are database people. The write-ahead log is on durable storage. In other words, virtually every darn thing a database does goes through this chasm between storage and compute. Okay? And if you don't bridge that with intelligent caching, you are simply not going to get the performance people expect. And here's the truth. The cloud may be wonderful and all, but if I can't get the performance I'm used to, I'm not going to move my workloads, right? So that's the conundrum. And when you look at the different workloads, the kinds of patterns you see for analytics, the kinds of patterns you see for OLTP are vastly different. Okay? Historically, even when people use the same database software for an OLTP workload and an analytic workload, they set them up night and day apart in terms of how they're tuned, configured, right? For reasons like this. And so making these cloud native is a journey, not something you're going to do overnight. Let me give you a sense of what I mean by the memory hierarchy. What you see up there at the very top, there, that's one machine, one virtual machine, okay? Queries are run here. The buffer pool is the local cache of the database. Main memory, this is the buffer pool extension. But basically, this is data stored by the database close to memory, okay? And memory and SSD, main memory and SSD. The amount of data you have, as you go from closer to farther, the amount of data you can store for a given dollar increases exponentially. Okay? So you want to store as much as possible here. Data here, you can go up and down elastically. The number of compute VMs you can change up and down elastically. But getting from here to here, you need to bridge. All of this is overhead introduced transparently by the system. Okay? All right. And if you look at how you play the same game with respect to the log, even more complex. I'll hide this detail from you. But the bottom line, if you want to get into the game of taking a modern OLTP system and making it cloud native, what I said earlier, you can have as many compute resources as you want for your workloads, as much data as you want for your workloads. To make that real, there's this whole complicated infrastructure hiding in the middle. And that's the magic in making something cloud native. Okay? You're hiding the data as well as all the intermediate state of in-flight transactions. When you do this, some magical things happen, right? For example, size of data operations, recovery. Historically, if you have to recover a terabyte database, you can go to the nearest coffee store and get a cup of coffee. A 10 terabyte data set, you can go to Columbia, pick your beans, you're good. With these architectures, because the data is made three-way durable, if something goes wrong, all you do is bring up another VM, attach it, life goes on. Constant time recovery, right? There are these unforeseen byproducts, historical problems we have been challenged with for 20 years, right? But the core reason for doing it is cloud elasticity, cloud native architectures. Other things are happening. I already mentioned geo-replication. The nature of the cloud, that all the public clouds have locations across the world, means you can easily write to an abstraction that ensures your data is synchronously and transactionally replicated worldwide. Okay? Earlier, companies like Yahoo built bespoke systems. Today, you can go and rent these on any public cloud. Let's take analytics. If you take analytics, Microsoft is a gigantic internal user. Why? Take Bing search. Bing search today, if you search for slushies, you may get results like this. These results are not web pages, but information synthesized from web pages. Before you even get to answering a query like this, the entire web has been crawled. Information extraction on it has produced a knowledge base. You classify pages as websites. Within them, menu pages. Then you extract the actual menu items. You have a knowledge base. You have a structured knowledge base describing the content on the web. And when someone searches, you try to infer their intent. When you say smoothies and you're driving by Houston, I know you're not looking for a grocery store based on past searches and what people clicked on. You're most likely looking for a juice bar. Understanding your intent, understanding the content that best matches your intent, the right algorithms to do the ranking. Should I weight Yelp ratings higher than proximity to the store? All of this iterative experimentation. Okay? All of this happens on our internal analytics cloud. So this is, think of it as Hadoop clusters on steroids. The largest Hadoop cluster I'm aware of is about 4,000 or 5,000 nodes at companies like Yahoo, Facebook. Our smallest cluster is about 43,000 nodes. Okay? Our daily I/O is 3-4 exabytes. Exabytes. The total amount of data is in the double-digit exabytes. And in all of this comes GDPR. Okay? When you search, your search history is recorded. It's used to build ad profiles. And I show you those show you ads using those ad profiles. There are dozens of teams, thousands of developers involved in all of this. And here's what GDPR says. Oh, by the way, there's tons of machine learning going on, as you can imagine. Across all of this, GDPR says, if you were to come to Microsoft and say, what do you know about me? There's a dashboard. Oh, I don't like the fact that you know my search history. Forget that. That's a data service request. Microsoft has 14 days to get rid of all your data. All the data is in HDFS, immutable files. Oh, well, that's Microsoft's problem. The fact that your 3 search lines are interleaved with hundreds of millions of other users' searches, the European Union does not care. Okay? All right, we'll batch all the delete requests in the past 2 weeks and make a pass, rewrite everything. Happiness? Not quite. Remember those ad profiles? If I built an ad profile using a search that is to be deleted, I must trace every such ad profile and delete that. Lineage. Across teams, across various query and machine learning pipelines, right? At a fine grain. All right. Let's look at the other family of data analysis, warehouses. These are classic MPP systems. Unlike the data lake that I described a while ago, you don't have the wide variety of data. You don't have the kind of scales we talked about. But you have blazing, fast, relational queries, highly predictable performance, deep integration with the SQL toolchain. Okay? If you look at the architecture for these, they are old school, the old generation. If I take the compute pool, there's cached copies of data. But also in here, right, each of the machines has some transactional state. So if one of the nodes fails, I basically am constrained in what I can do until it comes back up. This vastly limits my elasticity. Similar to the story you saw earlier with the OLTP systems. The newer generation, I predict, will be, first off, much more massively parallel, designed to run on thousands of nodes, not tens, and completely separating the compute from the storage. All of the transactional metadata, the transactional capabilities will be logically separated. In other words, cloud native analytics should be around the corner. If you take this, the numbers we are talking about behind these market segments are enormous, right? The two segments, data warehousing and data lakes, I think are going to collapse. They're going to become one. OLTP, NoSQL, while they'll remain distinct technically, increasingly people want to access all of this data together, right? And the reason for that is, in the context of the overall complexity of how many different data types, how many different repositories, how many different locations for data, the job of actually using this is becoming unmanageable, right? So we are today in a state of flux where this whole thing is almost reaching a singularity, and the forcing function behind a lot of how we are changing the infrastructure is the cloud. And that separation I talked about earlier is happening across the board, right? And as this happens, as every one of these classes of systems separates state from compute, there could also be powerful new ways to bring these together, right? And if that happens, hopefully, we will see a much simplified world where OLTP and analytics comes together. So I'm almost out of time. I will just say this. The part that ultimately will make the biggest changes over the next 2 or 3 years, and it will go hand in hand with this simplification, is governance, right? The thing I urge you to think about when you are thinking about how to build a better model, to some extent, you're like the Manhattan physicists. AI is here. You can have debates about whether it's good or bad societally. Doesn't matter. It's here. As individuals, how do we work to inform the right legislative controls over data? I can find out more about you on Facebook, most likely, than by getting a subpoena on your home, all right? And frankly, I find it appalling, the amount of information people cheerfully put about themselves out there, right? But if you look at active collection of data for various, in themselves, perfectly reasonable purposes, taken together, there's an enormous amount of personal data out there. As you put medical information out there, as you start doing gene sequencing and put it out there, the kind of information gets ever more personal, okay? And we need to protect this. Companies, as they start to collaborate, are trying to protect their IP. All of this means, and hopefully if there's one thing I've convinced you of, managing all this data in this emerging world of cloud is going to be complicated. Mostly it'll be people like me doing it, not you, which means you need to be very nervous, okay? You need to be thinking about, hey, is my data being handled the way it should be given its nature by these bozos out there behind some cloud, right? And to do that, it's got to be a joint enterprise across everyone, the users, the regulators, and the techies. So with that, thank you.
Couple of questions.
Yes.
Couple of quick questions.
Yes, please.
How do you view Google's Spanner and I guess it's the open source Cockroach DB attempt to connect relational databases with distributed transactional databases. How does that fit into this picture? Do you see that as a misguided attempt to do this, or?
Yeah. Let me talk about Spanner. We can take Cockroach offline. If you take Spanner, basically it does something unique. Transactions across geo-regions, okay? Technically, it's a tour de force, and it's relying upon very proprietary, very high-end networking investments they have, okay? Frankly, we haven't seen much real need for ACID transactions across geolocations. ACID transactions inside a data center, yes, lots of people ask for it. You don't need Spanner for that. Many other systems do. Will the world change? Maybe, right? But in return for that, there are other things, full SQL compatibility. If you want to take existing SQL workloads into the cloud, that last mile of compatibility becomes super critical. These are things that Spanner is lagging on. So it depends on your workload. Other questions?
Another question? So I'll ask a question.
Please.
How much of what we want, like provenance and the different type of data, much of it you say is still just data. How much of it can just be pushed into the database? We already have rules. I mean, there are lots of machinery already exist in the database, rules which you can implement policies and triggered operation. How much of it can we just implement inside the database rather than going and doing it from the outside?
So I think it's a matter of what we mean by inside the database, okay? At some level, all of the metadata that you're gathering, if I say that you ran this particular program, in fact, I skipped some slides, we can analyze the program, syntactic analysis, know that these inputs are flowing through to these outputs. So when you run this program, I know the edge that's going to be derived provenance-wise. I know which program ran when, following which other program from the telemetry. So the actual provenance edges, we in fact automatically infer. And when we infer, where do we put them? In the database. To your point, the provenance data is simply metadata that is harvested and stored in the database. But then think about the various pieces I just described. You need to have telemetry in a way where the timestamps of different parts of your system are synchronized. So before, after, when those line up. When you think about extracting the provenance from running a given program, if you run SQL, I know how to do it. If you run Spark, I can write a program to do it. If you're writing data scripts in Python, I need to be able to infer what's going on there, right? Every new modality of transforming your data, you need to somehow be able to express and capture automatically this provenance. Then all of it needs to be stitched together. And when you do, that's really the core underlying metadata. Beyond this, if you look at the kind of access control people are asking for, from the standard relational RBAC, now they are saying things like, Raghu can see all the data, but Moshe can only see the data that's marked non-PII. What is PII? We scan the data and run a classifier that marks certain items. So these are tag-based access controls. The kinds of things, the kinds of policies people are trying to express. As data is processed, as you track the provenance, some rights travel with it, right? If this data is considered secret, then no matter what you derive from it, everything downstream is considered secret, and you need to have the appropriate level of clearance. To come back to your question, every single example I gave, to enforce it, abstractly, you harvest the metadata, store it in a database, and then enforce a policy by checking that metadata. And so the database is used as a mechanism in all these scenarios. But each of these scenarios involves net new work that we don't have in place today.
Thank you. Let's thank Raghu for a very inspiring talk.